Okay, so now we're going to talk about the first in a series of laws that govern the behavior of gases. So this law is called Boyle's law, named after an English scientist. And basically, this is the law in words. At a constant temperature, the volume of a fixed mass of gas is inversely proportional to the pressure of the gas. All right? Now, we can state this mathematically in this way: the volume is inversely proportional or directly proportional to 1 over P. Another way of stating it, which is probably the most convenient, is P1 V1 is equal to P2 V2. Basically, what this is saying is that the product of the pressure and the volume is constant. All right? So this equation is more useful because if you, for example, have a gas where the pressure is P1 and the volume is V1, and let's say you change the volume to V2, you can easily rearrange this equation to calculate P2. All right? So this is showing you the graphical representation or relationship between the two. As you can see here, as the pressure decreases going down, the volume increases, or vice versa. All right, so that shows you in a more graphical sense the relationship between the pressure and the volume. And this is showing you a diagram which illustrates what happens when you change the pressure or change the volume, what happens as far as the pressure is concerned. So here we have a gas trapped in a container where the pressure is 1 atmosphere and the volume is 1,000 milliliters. So the PV product would be 1 atmosphere times 1,000 in that case. And then all of a sudden, you decide to increase the pressure, actually double the pressure from 1 atmosphere to 2 atmosphere. And there's a corresponding decrease in the volume from 1,000 mils to 500 mils. And when you take that pressure volume product, 2 times 500 mils, you're going to get the same as 1 times 1,000, which is 1,000. And if you apply more pressure to double it further from 2 atmospheres to 4 atmospheres, the volume will be reduced from 500 mils to 250 mils. And again, the pressure volume product will be the same, work out to be the same as the previous two. All right, so that shows you again the inverse relationship between the pressure and the volume of a gas, provided, as we said before, that the temperature is fixed and the amount of gas is fixed. All right, so we can use Boyle's law to solve a problem such as the one that you see here. Question says an 8-liter sample of nitrogen is at a pressure of 500 torr. What must be the pressure to change the volume to 3.00 liters? So in this case here, let me just rewrite the law here. It's P1 V1 is equal to P2 V2. And in this question, they're asking for the new pressure. So the question is asking for P2. So what I would do is rearrange this to get P2 is equal to P1 V1 over V2, and then I would put my numbers in. Now the initial pressure is 500 torr. The initial volume is 8.00 liters. And the final volume is 3.00 liters. All right? So the liter units cancel out. So your answer will be left in torr units. So what I would do is use my calculator to find, okay, so 500 multiplied by 8 divided by 3. Okay, so according to my calculations, okay, let me just make a change here. I'm going to assume that there's a decimal point here after the 500. So that would make that 3 sig figs. So this would be 3 sig figs here. So the answer when expressed to 3 sig figs would be 1330 torr. All right. Okay, so that's how we do that. Now let me just say something at this juncture. Whenever you're using this law, let me go back to this function here. Whenever you're using this law right here, it does not matter what the pressure units are for P1 and P2, and it does not matter what the volume units are for V1 and V2. What is important, however, is that the units of P1 and P2 are the same, and the units of V1 and V2 are the same. All right? So in this particular problem, it turns out that the units of V1 and V2 are the same, which is liters. And the reason why I mentioned that is because in some cases, you may get a question where the volume for V1 is given in, let's say, liters, and in the case of V2, it's given in, let's say, milliliters, all right? In which case, you'd have to do some conversion. You have to either convert the liter value to the milliliter unit or the other way around before you can put the numbers in and work out the problem, all right? So that is something that you need to be aware of. Okay, so that's that example. So the next law we're going to look at is Charle's law. And Charle's law is one that describes the relationship between the volume of a gas and the temperature. And what you see here on the screen is a plot of the volume of a gas, in this case methane, but it could be any other gas, versus the temperature expressed in Celsius. And what you'll find is that there's a straight line relationship, and you'll notice that the line will extrapolate. If extrapolated, will cut the x-axis at minus 273 degrees Celsius. All right? Now, what this represents is basically a situation where if the gas existed under lower temperature or very low temperatures, it will contract to a volume of 0 when the temperature reaches minus 273 degrees Celsius. And that's a very special situation, which, as far as I know, has never been achieved, but it's just a theoretical concept, which basically suggests that at that temperature, the gas will have no volume. In other words, the gas particles will have no energy. Basically, all the gas molecules will just collapse into one very, very tiny space. All right. So this is Charle's law in words. It says that at a constant pressure, the volume of a fixed mass of gas is directly proportional to the temperature, but the temperature must be expressed in Kelvin, and that's very important. All right. So you can express it mathematically this way, or you can express it this way, which is more convenient, because in this way, if you know any three of these terms, you can manipulate the equation to determine the fourth term. So remember, as far as the temperatures are concerned, they must be expressed in Kelvin. It doesn't matter what the volume units are, as long as they're the same on both sides. But for temperature, the temperature values must be expressed in Kelvin. All right? And this is showing you basically the effect that the volume has, or the temperature has, on a volume of gas. So here we have a gas trapped in a container. You have a free floating piston here. So we're assuming that there's no friction that exists between the piston and the walls of the container. So here we have the gas, let's say under normal room temperature conditions, same pressure being applied. And therefore, when you heat the gas, then the particles start moving around more energetically, and that forces up the piston to a corresponding increase in volume. All right? So that's basically how Charle's law works. So we can use Charle's law to solve a problem such as the one that we see here. It says that a 25, or I should say 255 mil sample of nitrogen at 75 degrees Celsius is confined at a pressure of 3.0 atmospheres. If the pressure remains constant, what will be the volume of the nitrogen if its temperature is raised to 250 degrees Celsius? So this is obviously a Charle's law question, because they gave you the initial volume, the initial temperature, they gave you the final temperature, and they said that the pressure is constant. So even though they gave you the value of the pressure, that doesn't really come into play because the pressure doesn't change. So therefore, we write down Charle's law in the way that we're accustomed to. So Charle's law, hold on 1 minute. So Charle's law says V1 over T1 is equal to V2 over T2. Okay, so if you want to find the new volume, which is what the question is asking for, I would multiply both sides by T2. And if I do that, I'm going to end up with V2 being equal to V1 T2 over T1. All right, and then I'll plug in the numbers. So to calculate V2, V1 is equal to 255 mils multiplied by T2. Now T2 is the second temperature, which is 250 degrees Celsius, but we have to add 273 to convert it to Kelvin. All right, and then below we're going to have T1, which is 75 degrees Celsius, but we have to add 273 to convert it to Kelvin. So what I would do is work out what's within the parentheses first. 250 plus 273. So that gives 523 Kelvin. And down here it would be 75 plus 273. And that gives 348 Kelvin. And then I'll do the rest of the calculation. So 255 times 523 divided by 348. And the answer I get is 383 milliliters. 383 milliliters. And that's how you do that. All right. So that's basically Charle's law. All right. So the next law we're going to look at is Gay-Lussacs law. And this law says that the pressure of a fixed mass of gas at a constant volume is directly proportional to the temperature of the gas. So you can express it this way or this way, which again is more convenient because, again, if you know three of these terms, you can find the fourth one. So let's apply that. And also, let me say here that the temperature must be expressed in Kelvin, just as in the case of Charle's law that we just saw. All right. So let's look at this particular example. It says at a temperature of 40 degrees Celsius, an oxygen container is at a pressure of 2.15 atmospheres. If the temperature of the container is raised to 100 degrees Celsius, what will be the pressure of the oxygen? So this is, whoops, okay. So let me start here. So again, it's P1 over T1 is equal to P2 over T2. And the question is asking for the new pressure. So we can rearrange this to get P2 is equal to P1 T2 over T1. So P2, put the numbers in. So P1 is 2.15 atmospheres times T2. Now T2 is the new temperature, which is 100 degrees. But we have to add 273 to that to convert it to Kelvin. All divided by T1, which is the initial temperature, which is 40 degrees Celsius. And we add 273, let me take that out, Kelvin, to convert that to Kelvin. And then the top part works out to be equal to, this part here in the parentheses, work out to be equal to 373 Kelvin. The bottom part here works out to be equal to 313 Kelvin, right? And the Kelvin units will go. So your units would be in atmospheres in the end. So 215 times 373 divided by 313. And according to my calculation, this works out to be equal to 256. No, this can't be right. Let me do this again. 2.15 times 373 divided by 313. 2.56. Okay, I knew something was wrong. Okay, so 2.56 atmospheres. All right. So that's how we do that. All right. So basically, those are the first three laws that we were introduced to. So now this begs the question. Okay, so now that we have those three laws, if you'll notice, in those three laws, there are things that have to be held constant. In the case of Boyle's law, it's the temperature that is held constant. In the case of Charle's law, which relates volume to temperature, it is the pressure that is held constant. And then in the case of Gay-Lussacs law, it is the volume that is held constant, right? So basically, we can only, according to those laws, look at the variation of only two things. But what if all those three terms vary, right? What if you have a gas where the pressure is P1, the volume is V1, and the temperature is T1, and then you change conditions such that you end up with a new pressure, P2, a new volume, V2, and a new temperature, T2. So basically, we have what is known as the combined gas law, which takes care of all of that. And this is what you see here on the screen. The combined gas law says P1, V1 over T1 is equal to P2, V2 over T2, right? So this is a law that you would apply if everything changes, right? If the pressure, the volume, and the temperature of the gas changes, then this is a law that works. It's a combination of the Boyle's, Charle's, and actually Gay-Lussacs law, even though it's not listed here. All right, so it's very easy to use. If you know algebra, then you can use this equation. You can use it to find, one term if you know the other five, and therefore it's very simple to use. So I don't have an example of that, but of course you get to do that in your exercises. Okay, so let's talk about standard temperature and pressure. Very often in discussion of gases, in order to make meaningful comparisons, we have to make sure that we are talking about the conditions being the same for all the gases in the discussion. So therefore, what was decided was that it was adopted that one particular temperature and one particular pressure will be what is considered to be the standard temperature and pressure. And therefore, once those conditions are held, then we can make meaningful comparisons between gases in terms of their other properties. So standard temperature was decided to be at 0 degrees Celsius, which is 273 Kelvin, and standard pressure is decided to be at 1 atmosphere, which is the same thing as 760 torr, which is the same thing as 760 millimeters mercury. So whenever you see the abbreviation STP, that stands for standard temperature and pressure, and therefore you should immediately understand that these are the conditions that we're talking about. Okay, so let's look at this example. It says a sample of hydrogen occupies a volume of 465 mils at STP, and if the pressure is increased to 950 torr, what would the temperature, and if the temperature is decreased to minus 15 degrees Celsius, what would be the new volume? Okay, so this is a bit long-winded. So what I would do is, just to make things more clear, I'd write down the different terms that one can easily identify in this question. So the initial volume, V1, that is equal to 465 mils. The initial temperature, it says STP, so that means the initial temperature is 273 Kelvin. The initial pressure, so that's T1. The initial pressure P1 is the standard pressure, which would be equal to 760 torr. The final pressure, P2, is equal to 950 torr. The final temperature, T2, is equal to minus 15 degrees Celsius, but we have to add 273 to that to get it to Kelvin. So let me do that calculation quickly. 273 minus 15, so that gives you 258 Kelvin. 258 Kelvin. And the question is asking for the new volume V2. All right. All right, so remember now the combined gas equation is P1 V1 over T1 is equal to P2 V2 over T2. What the question is asking for is V2. So what I would do is to isolate V2 by itself on this side of the equation, I'd multiply both sides by T2 and divide both sides by P2. Because when I multiply both sides by T2, the T2s will cancel here and here, and the P2s will cancel here and here. So now we're going to end up with V2 is equal to, oh, by the way, I need to put P2 down here. So V2 would be equal to T2 P1 V1 over P2 T1. And then all I would do from here is put the numbers in. So T2 is 258 Kelvin times P1, which is 760 torr, times V1, which is 465 mils, all divided by P2, which is 950 torr, times T1, which is 273 Kelvin. The torr units will go, the Kelvin units will go, and the only unit remaining will be the milliliter unit. So 258 times 760 times 465 divided by 950 divided by 273. And the answer I got is 352 mils. All right. And that's basically how you would apply the combined gas law to solving a problem of this type. All right. Okay, so we're going to stop here. The next law we're going to look at in the next video is Dalton's law of partial pressures. All right, so until next time.